So we're going to do boundary value problems today. By the way, we're off-roading today. This lecture is not in the notes like everything else. I know. Crazy. Okay, anyway, I'm going to write this up, and I will probably have it up within the next couple of days. We'll see. But, of course, it's available online, and I might email you these codes, or I might just try to type it up quickly so then I can just send it all at once to you. So we're going to talk about MATLAB's boundary value problem solver, okay, that's built in, and how to use it. So what we have right now are two techniques. We have a techniques of shooting, right, where you go from one end, you shoot across, try to land on the two boundaries. You also have the idea that we talked about last time, which is you can discretize. You can take this domain that you're solving for and just use what the definition of derivative, use these slope formulas essentially, to discretize the domain and set up a giant matrix problem. Now, in general, when it's nonlinear, it's no longer just AX equal to B, but some nonlinear system of equations to solve. Okay? So you could program that up, but in fact, MATLAB's already done it for you. So we'll learn how to see how they think about this. We're going to start off with a simple example. Okay? So here's the example we'll start with today. This with the following boundaries. We'll solve it, let's say, from x is an interval between 1 and 3. And my boundary conditions will be the following. Y at 1 will be equal to 3. And y at 3 plus 2 y prime at 3 is equal to 5. Okay, I just made that up, right? Okay. Okay, so we go, okay, how to solve this. Now, this is a simple enough problem. I could do it analytically. I know how to solve this thing. I could write down solutions by hand, okay? So to some extent, what we're going to test is, can I take something like this, and can I put it into MATLAB, have MATLAB solve it for me, get out this solution I want? Okay, so as before, the first thing you're going to have to do is you're going to have to transform the second-order equation into two first-order equations. Second, you're going to start thinking about these boundaries as functions that need to be satisfied. Okay? And so what we want to do is set this up. We have the equation itself and the boundaries. These are two things that have to be satisfied. So I got to satisfy this, I got to satisfy that. So we're going to tell the program how to do this. So first, let's break it up into a system of first-order equations. Right? So first I might do something like this. I will define y1 to be y and y2 to be y prime. Okay? So then, again, let's just go through this process again. Take the derivative of both sides. You get y1 prime is equal to y prime. y2 prime is equal to y double prime. And the first equation says y1 prime is equal to y prime. But wait a minute. Y prime was just y2. So I have an equation, y1 prime is equal to y2. And then I have y2 prime is equal to y double prime. But what's y double prime? Well, I know what that is, because that's in my equation. So y double prime, I can come back over here and look at it here. Y double prime is 5 minus 3y prime minus 6y. Okay? So I can move this to the other side. And if I do that, I get 5 minus 3y prime minus 6y. But y prime is y2, and y is y1. So these just get traded out for a y2 and a y1. There it is. First order form. We're set to go. We're going to use that. What about the boundary conditions? We also want to state the boundary conditions in the following way. What we want to think of is I have some boundary condition on the left. Let's call it f of L for left. In this case, it's 1. I want to figure out how to write this as I have some conditions on the left, some function. What's that? The left. And the right is 3. Then function on the right. So what are these two functions? Well, from here, they're pretty simple, actually. I want this something equal to 0. So what I have over here is y at 1 is equal to 3. Well, y is what? Y is y sub 1, right? I'm going to trade that out. I'm going to say that I'm going to write it in terms of y1 and y2. And so my boundary conditions are the following. On the left, I'm going to have y1 minus 3 is equal to 0. That's my boundary condition at 1, my left boundary condition.
Sorry, you make them equal to 0 because that's the convention for the
That's the
solver?
convention for the solver.
Oh, okay. That's
Smooth the 3 over. Yep. Okay? I want some function that's equal to 0. The other one, so if I move that over, the other one here, I just move the 5 over. And what I have is y3 plus 2y prime at 3 minus 5 would be equal to 0. And so I know that the y is y1, 2, y prime is y2. So what I really get there is y1 plus 2 y2 minus 5 is equal to 0 at x equals 3. So I've rewritten the equation and the boundary conditions. Okay? So that's it. Everything's now in terms of y1 and y2. I'm trying to satisfy this and this simultaneously. Okay? All right. So this is the information that MATLAB needs from you. What you're responsible for is giving it the right-hand side, just like in the ODE solvers, right? It assumes that you have a dy dt equals some right-hand side. Here's your right-hand side right there. MATLAB needs to know that. It also needs to know what these two functions are. So you have to give those as well.